Welcome to continuous performance monitoring of a distributed application. My name is Diana Yurieva.
My name is Ashish Srivastava.
And today we are going to talk about extreme performance monitoring. So let's start with the goal of this session. What is going to happen in the next 1 hour? Well, we are going to tell you how to arrive at a solution for extreme performance monitoring. We're going to share what worked for us and what you can apply in your own environment. So our solution, actually, we categorized it in two broad components. The first one is design patterns, which is way you can modify your software to incorporate monitoring into your software. And the thing which concludes it is the tools. And what we would like to communicate to you is that we're not going to sell any products. This is not a sales pitch. If we mention some names, it's because we thought they are useful and maybe you will find them useful as well. But definitely this is something you can apply to any Java distributed system. This is not going to be about a particular product. So what makes our solution interesting? Well, we've outlined these three qualities which are going to make our solution stand out from some other solutions out there. The first quality is that we are interested in something which is continuous. We don't want a monitoring solution which is used only for debugging, profiling, short runs in staging area. Our solution is going to be always on. It will be running 24/7 in production mode. We will be able to use it in development as well, but our goal is to have this solution in production as well. Our second quality is that we want the solution to be lightweight. Well, as you saw, we are about extreme performance. If we introduce monitoring and then performance goes to mediocre performance, that's not what interests us. So we definitely want a solution to be lightweight. And by lightweight, I mean it will take no more than 1% of the overall processing. And the final quality will be that our solution is recordable. By recordable, we mean that you will be able to share it with others. You will be able to refer it to another point at another point. All these qualities altogether make the monitoring solution more valuable. So how are we going to structure this presentation to talk about all these things? Well, we are going to start a little bit about our use case. After that, we're going to proceed with a very detailed overview of the software patterns. We're going to finish the presentation with an in-depth description of the tools we use, and then some pitfalls and advice, things we wanted to share. After that, we will open the floor to the questions and answers. So let's start with use case. And in order to understand our use case, you need to know about our software. So what we are called is Oracle Billing and Revenue Management Elastic Charging Engine. I'm going to call it EC from now on for obvious reasons. Has anyone heard about it? Okay. Has anyone working in telecommunications? All right. Seems like the majority doesn't know what it is and doesn't work into telecommunications, so I have to spend a couple of minutes on this slide. So Oracle Charging Engine, EC, you haven't heard about it because it's not something you can buy in Macy's or Best Buy. However, believe it or not, you actually interface with it on a daily basis. That's because software like Elastic Charging Engine is a software which your telecommunication operator is using. Every time you make a call, this software checks your balance, verifies whether there are enough funds on your balance, and then decides whether your call can go through or rejects it. And this, of course, extends beyond calls. We rate your data sessions, your short messages, everything related to telecommunications. So that's what we mean when we say charging, real-time charging. And what makes it interesting is that in prepaid cases, it's of course a lot harder because we may have to make this decision in real time. We have to check your balance, see immediately whether there are enough funds of your balance when you start your call, and well, we have to actually finish your call the moment you run out of balance. So that makes prepaid charging a lot harder than postpaid charging, where you can maybe just batch something in certain hours, but real-time charging with prepaid charging has to happen in real time. So that's what it means, 100% real-time charging application. Hopefully now we're all on the same page. And what makes ECE interesting and why we are going to use it as an example throughout all these presentations are these three factors. Well, first of all, it's written in Java. That's pretty clear. Second of all, we are a distributed application. To achieve performance, you can no longer do in a single process, right? So we use the technologies called Oracle Coherence and Oracle NoSQL, but as I said, our patterns will apply to every distributed technology out there. And finally, what will make our monitoring solution really interesting is elastic charging engines focus on extreme performance. Our latest benchmark was 1,000 operations or calls per second per core. So this software, its main selling point is its performance. Performance is what differentiates it from other competitors offering, and therefore our monitoring requirements will be particularly stringent. So let's see what are the conditions in which we operate, because these shape our monitoring requirements. Well, first of all, we have expectations of low latency. Well, clearly, all of you guys, you want your calls to go through fast. You're not happy if, the little lady goes, dials some number, connects. So you want just everything. You want tweets immediately to be published. You want calls to be immediately connected. But it actually goes beyond that. And you might not realize that the telecommunications industry has very stringent requirements of the worst case latency. In other words, we never know which call is an emergency, and we just cannot afford to have certain calls which get rejected because of performance issues or just get accepted but with a very long latency. The second factor is overall heavy throughput, heavy system load. Again, nothing new. In developing markets, more and more people get phones. Here, I'm sure everyone has a smartphone, but then you guys start to get more devices. So overall, the load on such a system as elastic charging engine is only increasing with time. And then there are some factors which are just linked to the nature of our application, to its technology, the fact that it is distributed, and the fact that it uses a multi-level software stack, which, as we said, is Oracle Coherence and Oracle NoSQL. So what is it? What do we want? Well, we want to monitor our performance primarily. And the key thing is that we want to get key insight about latency and throughput. And latency and throughput, they are pretty generic performance indicators, which I'm sure you know about. But for us, they map into very tangible business KPIs. Latency is the time your call gets to be established. And throughput is the number of people who get their calls established at the same time. And believe it or not, we care about every single call of yours. We never know which call is going to be an emergency, and if you're calling 911, you don't want to be in that 1% which happens to fail or have an extremely long response time. Other factors which we would like to see from our monitoring solution is that we would like to view our latency and throughput over time. We're not happy with just a snapshot of what happened at a particular moment. Some of the nice-to-have features, they are reporting. We'd like to share the resulting reports with our colleagues, managements, and customers. It would be nice to have some bottleneck detection so that we can tune certain parts of our application proactively. And finally, we'd like to get the view of a system as a cohesive unit. This might not be immediately obvious, but once you move away from a single process and you distribute your application, you have multiple machines, multiple technologies, it actually becomes a challenge. How do I collect data from all these little moving processing parts, and how do I get it back to myself in a single view? So this is another requirement of our monitoring solution. We have a couple of non-functional requirements. The main requirement of course, being the performance. If the system is incredibly heavyweight, it's not going to work for us. We want a solution which does not impact our performance significantly. Some other nice-to-have features would be the usability. We want it to be easy to use. If it takes 20 screens, 20 commands, 20 PhDs to set this up, monitoring up, it's not going to be very valuable. And then the final quality is a separation of concerns for the software purists among us. So monitoring is a cross-cutting concern. It's something which affects every area of our application, but at the same time, it's not our main business logic. So we want to address this cross-cutting concern elegantly. We don't want our code to be tangled or some pieces to be duplicated. So we want to apply the right software techniques to address the separation of concerns. So now you know what our environment is and what is it that we want from the system. Finally, it's time to tell you how did we achieve these monitoring requirements. And stay tuned. I'm switching to Ashish, and he's going to tell you about the first part, the software patterns.
Okay, thanks, Jana. Can you hear me all right? Yeah? Okay. So, over the years as Java graduated from a single instance, single host type of application to something which is clustered, now massive clusters with peer-to-peer clustering protocols, and in a distributed computing environment, the topic of monitoring not only became challenging but very important. And when we come to sessions like JavaONE or similar, and we come across a new tool or the previous tools that have evolved into new directions, new functionalities, and we take those tools back home, try to use them, but somehow we still find that there's something missing. And it's supposed to be like that because what's typically missing are your application KPIs, your key performance indicators. So off-the-shelf software's monitoring, it's very important that you choose the right tools, but it's also important to believe that that will not be sufficient, would not address all your problems. And that requires that you build monitoring into your system. So there has to be a custom development that is needed. And like performance is not an afterthought anymore, you have to think about performance in your system. Monitoring as well, you have to build that inside out in your application. And once you have a mechanism to collect statistical data from your application, the next, of course, the challenge is how do you analyze that data effectively and present that data, which is useful not only for the development team, but for your business owners as well as for your customers. So that leads to this problem, that how do I incorporate collection of statistical metrics in your general processing? And the approach that we took is the term that I mentioned, the monitoring in design. You have to change your domain model to put monitoring in your system. It's not an afterthought. And before I dwell more in the details of how it works, this is my ultra-professional animation, but this is kind of an oversimplified form of what our product does. As Diana already mentioned, it's a clustering technology. It's all the nodes, they are using Oracle coherence on top of an in-memory data grid. From an infrastructure point of view, all these nodes are exactly alike with a little difference. We have some concepts of roles. Like some of the nodes, they perform the role of a processing node. These nodes manage the data that we load into coherence caches. And some nodes are just clients. Their job are very limited in their scope in a way that they only receive the network events and send it to for the processing. And people who are using Oracle Coherence or know about it would appreciate this diagram. So what do we do? Typically, we have a ECE client, which is kind of a functional client, not infrastructural client. It sits in a wrapper, what we call the network mediation. So if you're making a phone call or maybe tweeting right now or opening a data session, what happens is that network mediation is actually harnessing all these events that are coming to the service provider and sending to the ECE client for processing. But before we actually do anything about those events, what we do is we go through each request that comes to this client, we identify which customer these network events are meant for. And based on that customer data, what we identify is the partition. It's a distributed system. Partitions are spread across multiple nodes, multiple hosts. So we identify the partition number, the partition ID, which actually carries that customer data. And then what we do some kind of batching for the customers that are part of that partition and the members, the processing node that owns that data. So once we have this member information, we batch certain requests for that member, and depending on some ripe policy, like when that batch is ripe to be sent for the processing, we send it to that node. That becomes my request, right? And it's typical to our application what we do here, but certain activities happen on the processing node. And in your case, if you're working in a distributed environment, similar activities might be happening as well. So in our case, what we do is we debatch the request. We do some data lookups. We apply the tariff, which is the core of our charging domain. Of course, we save the call sessions that, making a call or you're tweeting, we save that session or certain information about that session. We prepare the response and we send it back. How many times we have seen a system where you send a request and you get a response back? It's very common, very common application. But how do we add statistical collection in this general flow? So what we did was we kind of loosely modeled it based on our general post office. You go to a USPS store, you buy an envelope, you buy a packet, you put your whatever letters or things that you're shipping, you put destination address, the from and to, and you give it to the post office for shipping. And what you get in return is a tracking number, and the tracking number already is on the package that you can use to find where that envelope is, where that package is. Is it through the sorting facility? Is it already has arrived in the destination city? Has it been delivered? And you get the acknowledgement back. So we kind of very loosely modeled this whole flow and introduced a concept called envelope. Right? So what we do is when we build a request, we put that request in an envelope, and this envelope flows through our system. Now, if you look at this diagram, you have multiple JVMs involved in a single flow. So the client is one JVM, probably on a different host. It sends a request over network, and if a network is introduced between a call, what will happen? Serialization. And then you deserialize that message on the processing node. You do some certain activities, and what happens is that envelope actually keeps on going across the system until you get the response back. So what a typical envelope contains? It actually contains three information, right? One, the first information is the routing information, which is like on your packet, on your USPS package, you have a from destination, those to and from destination, the addresses. That's a routing, where this whole envelope is meant for. The second component is, of course, the payload, what you're sending. In our case, it's a request. Without a payload, an envelope is functionally incomplete. The third, this model of introducing an envelope gave us an opportunity to introduce the concept of tracking. Right? So we have this tracking context introduced in the envelope, and as the envelope is flowing through the system, what we do is we update this tracking context. And how do we update that? We introduced a concept called chronicler. So as the request is sent, we add a chronicler. And a chronicler is like a passport, right? So you carry a passport, and the passport gets stamped wherever we want that passport to be stamped. So that passport that flows through the system, all the points wherever you need to stamp that passport gets marked, and marked with, in our case, the time points. And what we do is we garnish, we harvest that information on the client when the response comes back, and we introduce a concept of a statistical reporter that can harvest that kind of data. So from a very, in a simplistic approach, we introduce a concept of tracking context that flows through an envelope. The tracking context is a placeholder for all the chronicler information. Chronicler contains the time points, some other information as well. And then when it comes back to the response, we have a huge set of data, statistical data about per request. So we are very granular, and we can harvest that information through a statistical reporter. And if you expose that over JMX, that gives you a plotting capability. But one of the results could be something like this. You ran your product for a simulated period of, say, 3,600 seconds. You come across, oh, what's my throughput? 20,000 operations per second. And my average latency happens to be 50 milliseconds, right? Feel good. I'm meeting my SLA. But as you know, averaging something is deceiving. Averaging hides problems. You don't want to average and populate your benchmark and say, yeah, we can meet average latencies. Especially in the telco, as Deanna had mentioned, every call is important to us. So I cannot say my system meets 50 millisecond goal of latency, because maybe for the most part, the latency is about 3 milliseconds, but there could be few which is taking 500 milliseconds, and we need to track why those 500 milliseconds latency did occur. That leads to the second problem, like how do we get more granular information, and not only granular information, but how do I know what my latency is over a period of time? So we need another dimension of time against our statistical matrix. And the approach that we took was the statistical reporter has to be enhanced, because it has to be able to give the information about all this latency and throughput over a long period of time, and maybe live, always on, in a system which is always on. So that leads to something like this, and I oversimplified this. There are more APIs, more bells and whistles on top of it, but at the heart of this whole solution is a circular buffer. And circular buffer, what it behaves like is a wheel, a wheel which is moving. As the envelopes are garnished, it comes back to the client. We take offload the chroniclers, we put it in the circular buffer, and this wheel is actually while moving over a period of time. So what happens is the chroniclers are being added, it's full, and what we do, we offload the entire data that this circular buffer contains into a stat bucket. This is our own jargon, but a concept of a bucket. We offload the data to that bucket, and then it keeps on rolling on. It moves on, and the system keeps on putting chroniclers in this data structure. And what happens is when the stat bucket has all the collection of the data for a given reporting window, and then we can have the statistical reporter that can report on top of the data that were collected by the stat buckets. So another beauty of this kind of solution is, no matter how long you collect the data for a given reporting window, the size of the data that you collect is always fixed. So it's not like you are going to stress your heap just because you ran this application for 10 hours, right? So which is very critical. So we have a fixed data side, and based on how much data it typically contains, we can provision our heap. Second is, sample reporting. I would talk about why sampling is not, a good idea. But what we can do is when the requests are being chronicled, at that layer, we have an ability to sample the request. Maybe in some scenarios, for some people, we don't want to track 100% latencies. We just want to see, a general health. We can sample the request. Maybe 10% of the request, we want to sample how they are behaving. Not very useful, but it has to be built in our solution. So this data structure also gave us an opportunity that we could build a sampling on top of it. By the way, the chroniclers have the 100% request latencies here. And of course, once you have this data structure on top of all these APIs, you can expose the stats to JMX, and we can use that interface to represent our graphs and whatever tools that Deanna will talk about momentarily. Going back to this class, this is one of those slides that I was thinking maybe should we include it or not, because this problem can be solved in maybe 10 different ways. this is our solution. And not going into too detailed about this class diagram, but if you look at these classes, I'm not sure how legible it is from behind, but this presentation will be uploaded, so you can take a look later. But what happens is, you have a request, we have chroniclers, we offload the chroniclers to stat buckets. The stat buckets are associated to a stat reporter that do a continuous reporting, and we have some concept of nanoperiods, which measures the time that it took at each layer of your system in nanoseconds. So we have much more granular information. And some concepts of time points, which is associated with the label. And I will talk more about that in the next few slides. So this class diagram and the data structure together provided a mechanism so that we can not only collect the data, but we can do a continuous reporting over a period of time. And that led to something like this. Like, yeah, I have a much granular information I can collect. I can see my minimum, maximum, and average latency. And I can plot them, my throughput. I can see if it's erratic or if it's stable. Now, this is a very funny diagram that you have seen on your right. It has three different colors, blue, green, and red. These are typical 3 different network events that we get for the usage processing. You start a call, we get an initiate event that we process. Throughout your session, we get multiple events, update events. And when you hang up your call, we do a terminate event. And all these events, they have different signature when it comes to the processing time. So we measure these 3 events in a graph. And if you look at this, maybe some of these graphs, these are like a 10-hour period, but we do have an ability to drill down to a few seconds. And what happens is, like, most of the latencies are pretty acceptable. Some are maybe not acceptable, right here on your right. But the funny thing is, this is spike. If you're averaging it, if you're not tracking all your requests, that spike could be you making an emergency call, right? So you don't want that call to be dropped. And we have to have an ability to make sure, debug into our system, see like what really happened. Why did that spike was caused? So that led to kind of another problem. That you're plotting this data over a period of time, minimum, maximum latency, average latency, it's all good, but we need more granular information. The beauty is your domain model already supports a mechanism to collect the data, and now it becomes how you harvest the data effectively. So, the second goal, which kind of it's a real-time goal that our customers ask us to achieve, is like, okay, they don't care about which request failed, but from a product point of view, they want to make sure that can you guarantee that your 5 nines, 99.999% of the time, can you guarantee that your latency is less than a certain number? In our case, it's somewhere around 50 to 60 milliseconds. So forget about how do we achieve that. The thing is, we have to have a mechanism to prove that we can achieve it and show to our customers that here's a plot, here's my per percentile reporting, and I can prove we are tracking, we are not leaving any latency or any request behind. We are measuring every request in the system that's coming through. And we are measuring those, and we can plot where the most of these latencies fall in. So the approach, we introduce a concept of a range bucketing, right? So in the range bucketing, what we have are the predefined sets of latency ranges. So we have 0 to 5 milliseconds, 5 to 10 milliseconds, 15, 20, 25, up to the latency range which is relevant for us, say 60, 90 milliseconds. And maybe all the requests that took more than 500 milliseconds, which is too high in our scenario, could go into a generic bucket, right? So as the requests are coming in, we can plot this percentile at each layer of our system, right? So, and the good part about this solution is that unlike, the envelope that flows through the system, we are not adding any more data to be serialized or deserialized as the envelope is moving through our system. So the data already exists in our envelopes. what we do is, wherever the percentile breakdown is needed, we grab that report, but we grab those data, and we calculate which latency this request is falling in, which bucket, right? And so it's a fixed data set. Again, it's critical for predictability. And what we do is we in place put the latencies in that particular bucket. We just a counter, like this many requests took 5 milliseconds, X number of requests took 100 milliseconds. So once we have that, and compounded with different breakdowns, the stage breakdowns, end to end, when the client sent a request back and gets a response, we can track the latency percentile in a batch, which I mentioned earlier. Batch is like the batch of requests that we send to a member, and that is kind of our atomic unit of processing, or at the request level or at the server side level. So client sent a request, there's a network involved, but the request, when it comes to the server, how much processing it took on the server side when the orchestration happened on the processing node. So we have 3 different layers where this percentile reporting can be done. And we get something like this. It's like, okay, you have 99.999 percentile of the request are under 128 milliseconds. And this is a real data that we took from one of our test servers. And that gave us an opportunity to actually go and look into the tuning opportunities in our system. Now, in a distributed environment, there are so many factors that play in your latencies. Your how much heap you're consuming, the GC activities, all kind of activities. So what we do is serializer, for example. Like we are serializing the data and say, like, why are we meeting 128 millisecond 99.59 times of the whole period? There's something wrong, and that gave us an opportunity to see like what can be optimized, where in in which layer of the system can we actually dig more deeper and see where the optimization can happen. Can we optimize serializers? Can we optimize the deserializers? We use Oracle Coherence. They're something called a POF serializer, portable object format. If you're not already familiar with Coherence, I would like to take a look at it. So we have our own custom serializers, and we have full control of what kind of data that we serialize and deserialize. And of course, the other factors in the application that we can optimize based on this percentile. But the beauty of this tabular data is that once you have this collection of table entries, and you add a third dimension to this data, which is throughput. So if you capture the latency percentile against a varying factor of throughput, what can you do? You can draw a heat map, right? So this is, I admit, this is not the heat map that we plotted against our data. It's one of the sample heat map I took. But this is kind of, what is my varying throughput, what is my delay, and all these 3-dimensional axes, and we can plot the heat map. How useful it is? For many people, it does. It gives you a visual representation of where the most of the requests are falling in which quadrant. Okay, so well and good. That leads to another goal that introduced another software pattern in our system. And before I go too deep into this problem, I go back to the same analogy that I took for USPS, right? So everything is hanky-dory, system is working happily, and at one day you find there's a construction work going on 101, right? Or the new road has been built that your driver has to take. Or you hired a new driver and you want to track the performance of the driver or the impact of the construction work on 101. What's the impact of that particular change in the system? So this is, when we started with this challenge, it was more of a very developer-centric. We have continuous integration of our system. We do a continuous performance baselines. So, and we do this continuously as your developer is actually introducing new classes and new methods and maybe changing the current classes. And you want to track what is the impact of his or her change in the system. And we want to do that before that code is delivered. So this was the real challenge. But as we kind of produced the solution, some other goals from business comes and it's like, well, can we keep it on, all the time? Because this is a good statistics where we can say, from this stage to this stage, what is, how much, time my, requests are taking or my system is taking. And that kind of challenged us that you have to do something like this so that it does not impact the system, right? And one of the things that Diana mentioned in one of her slides is what is, the cross-cutting concerns, separation of concerns. And that kind of led us to start thinking about two solutions, annotation-based solution and aspecting the solution. Annotation in a sense that whatever we are measuring, whichever method we are measuring, we annotate that method. And the next slide actually describes a little bit more in detail. So we annotate that method and we create throughout our systems those critical points where we can annotate the methods which are critical, right? And then we can use some kind of an aspecting to limit the scope of the classes where those annotations actually take effect. And these annotations in turn are the points where the time points are added to our chroniclers. So as we build solutions over solutions, our domain model is not changing, right? We have already introduced the concept of certain data structures that can harness the statistical information, and now what we are building are all these reporting structures and how we analyze those information. So a typical class looks like this. So we have a preset, predefined labels, enums, and what do we do is whatever class that needs to be tracked and whatever method needs to be tracked, we annotate that method with this track annotation. We do have a couple of annotations, but for the sake of this presentation, I'm using this track. And this we have a concept of point label. How do I know this my information, how much time it took in this particular method? How do I uniquely identify that? So we label that information through a point label. And of course, then we can define a concrete aspect. We can define the point kit, what's the scope of my, and I can dig actually more into package details. So anything which is, Oracle communication dot blah, 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 enable them. Or we can be more precise and go to the class level that only, collect the data from this class. So what that gave us is exactly like this. It's a chronicler breakdown. It tells you how much the debatching activity took, how much the lookup of the referential data took, how much, when we impacted the balance, how much time it took. It's all in nanoseconds. How much time it took in saving the session and responding the session. And this is one of the mechanisms that really, really helped us to optimize our serializers. And it's like, yeah, everything is fine. Orchestration is not taking more than 3 milliseconds, 5 milliseconds. Don't get my number. I'm not claiming that. But it's like there's something happening on the network. And one thing that you need to look at is like, okay, what are you serializing? So once you go through all the attributes that you're serializing and deserializing, maybe I don't need this information and unnecessarily stress the network. And that led to another activities like, hey, can we use a linear data structure instead of what we were using? So this is a very, very powerful system that helped quite a bit when we were, working on this product, and we still do. As Diana mentioned, our SLA is to meet about 1,000 or 1,200 operations per second per core. So it's very, very extensive. It's a CPU-bound application, and when your application is CPU-bound, I will discuss more about what the challenges are, because now you are sharing your resources with other activities in your system, primarily on long GCs, and how do you relate and monitor those activities and still have a collective view of the system behavior. So with this, I give it back to Diana to talk about the tools that we were using, or still using.
All right. Thank you, Ashish. So these were some pretty complex software patterns. I'm glad you guys stayed through them. And Ashish walked us in great detail. In case you were worried, there is no more code snippets, so it becomes easier at this point. And well, what you've seen through the previous part is that we've built a solution which permits us to report every latency, to get a view into every request, every phone call. But in order to satisfy the performance requirement of this solution, being lightweight, I would like to stress that all these data structures, they don't grow over time. In other words, this little stat reporter, it doesn't store more and more and more data as you run continuous. In other words, this solution is still not complete, and we need one last part which will actually store that data and present it to us in an understandable format. So our approach to this is something we call the monitoring dashboard. This is a concept which most of you should be familiar with. It's just a performance dashboard which visually depicts all the metrics. And the technologies which we found useful, they are called GRDS and RRD. A little bit of in-house development just to glue this together. But the important thing is that most of the dashboard actually came by the goodness of this technology. So if you want to try it out, that's just something we would like to recommend. So here I'd like to actually break the flow of our presentation a little bit and show you the final result before I tell you how do we do it, so that you get an idea of how this monitoring dashboard looks like. And well, essentially it's just a web application, it's just one single web page which contains a lot of graphs. I chose the two which I thought are most representable. So the first graph I chose is the initiate latency. It's the most important latency for us because it's the latency your call gets established with. And what we see on this graph, flashing? Oh, no. Well, it's the graph on the left. What we see on this graph is that it's a result of a 10-hour run, right? And we see that we actually satisfy the requirement of the controlled worst case because the maximum latency, you see it's always in the 100 millisecond range. It doesn't go beyond somewhere. So knowing that our solution reports every latency and that we don't lose anything on the way makes this graph very powerful because we can use it to communicate to our clients. Hey, look at this. Our worst case is controlled within 100 milliseconds. Not a single request went beyond such a number. And then the second graph I include, because it's also very typical, is the JVM memory usage. So when you work at performance, when you look into these latencies, you need to correlate them with other factors, and garbage collection and heap management is one of such factors. So it's really useful to include such system metrics in your dashboard so that you can work with them in your analysis. And of course, it took our colleagues a lot of effort to actually achieve this kind of very managed Java heap, which in turn produced this very controlled latency. And finally, in the bottom, we always include the configuration. That's very useful so that we actually remember after a certain time what all these graphs were about. We know how many servers were used and what was the load like. So let's talk a little bit more about this monitoring dashboard and the technologies behind that. And you can use any technology which you like, but these are just the factors which we would like to stress out so that if you choose your own technology, well check if actually these factors satisfy the requirement. First of all, we got the view over time that's hopefully pretty clear and pretty straightforward, and you yourself saw how powerful the description of a latency is when you actually see it on a graph rather than if you just saw some text-based. Second thing, we included various metrics. Of course, most importantly, we want to see the metrics which Ashish told you how to build latency and throughput. But as I said, there are always those system-specific metrics which affect your application-specific metrics, and that's why you want to take a look into those as well. So you should probably include the machine-specific metrics, CPU, memory, network, delay, disk space, as well as some JVM-specific metrics, because hopefully you're all using Java. So thread count, garbage collection times, new thread creation. That's probably the metrics you would like to include so that your future debugging and tuning becomes easier. And finally, what makes this dashboard powerful is a consolidated view. As I said, we put all these graphs on one page, and then it makes it really easy to actually correlate the different factors. If you remember the graph which Ashish showed with the giant spike, well, maybe you need to look into your other metrics, maybe in the system metric, and see what happened there. Was it a full GC, or was it just a disk space, or something like that? So that really helps your performance debugging very useful. Some other qualities from a usability perspective is that the dashboard actually is easy to use. As I said, all of this comes mostly from the GRDS and RD technology, not very limited custom development here. So you just issue one command, and then the dashboard automatically starts to query all this data, collect it, store it, produce graphs. There was little involvement from our side to bring that, and that is, of course, very useful. And then the dashboard, it's a web application, so it's actually easy to share. As you saw, we customize it to include our configuration. And also, well, between ourselves, we can just send links so that someone else can take a look at the data we collected. But we can also print this page as a PDF, and that is pretty much cast in stone, and we can use it at any later time. Finally, some other useful factors about the monitoring dashboard. It stores data pretty much without losing precision. We have spent so much time building a solution which reports latency and throughput with precision, and then if you're storing solution pretty much dilutes this precision, that your purpose, it would be defeated. We need some ways of storing data which would maintain this precision. It also supports drilling down, something you might not be able to see from the screenshot I presented you. But actually, again, in case of spikes, you actually can drill down to that particular time period and say, hey, I want to see between this 5 minutes period, and this probably would help you to analyze the issues in more detail. And finally, the dashboard itself, it is lightweight. We actually run it on our laptops regularly. That's also very powerful because we don't have to wait until certain performance environment becomes available. We can start using it right away. And finally, as you saw, we were able to include some of our information. We were able to plug this dashboard to our own metrics. We were able to include configuration, so customization is always an important part for the monitoring solution. So that actually concludes our solution. Now you know the two secret ingredients which make it work. It's the patterns and the dashboard working together, which permit us to get detailed insight in about every latency and every phone call. But just before we finish, we would actually like to share some pitfalls and advice, something which we found useful on our way. We would like to let you know about this as well. So Ashish, please, could you tell us?
Yep. Okay, so pitfalls. Distributed monitoring is not same as a single JVM monitoring. There are so many loose factors that are involved in a distributed systems that do not even exist in a single JVM monitoring. And most of the monitoring tools that we use, they're all good, but they actually give you a harness the data that are local to a JVM. But you need to, whatever monitoring tool applications that you're using or you're building in-house, you need to make sure that you can correlate the events in one JVM on another. As I started out with, Java now is very extensively used in a pure clustered environment. Pure clustering goes beyond farming. What it means is that one activity that happens on one JVM is affecting the entire cluster. And we need to make sure that we map that activity and we can analyze that activity, that was the impact of that event on that node. So it's very important. I give you an example of a GC spike. One node under a full GC or a long mixed GC, and what happens is that node is suddenly not responding. And if the client is still receiving a stream of a high volume of network events, it's not able to send the request to that member. The requests are piling up on the client. And what you see is the overall system behavior, it actually goes in a degraded mode. So we need to be very, very careful about what we are monitoring and how effective it is to find and pinpoint the problem before you go ahead and solve it. Consolidated view is very critical, as I mentioned. You have to be able to relate the data, whatever solution you are using. The consolidated view is very, very critical. Second point that I would like to mention, and this may not be as critical but is very important, it's the consistency of tools that you are using and other teams or your customers are using, because if you can share a set of tools with your development team, with your QA team, with your performance team, what happens is it actually gives you a common language across the teams before you even release your product. And that saves many, many hours because from the specification, from the test specification point of view, they all speak the same language. So if some activities, some problems that happened in a performance test cycles, they can easily give you a test specification that developers, us, can actually go and try to reproduce it. Same language always helps, though not always critical. How many of your spouses allow you to take work at home? Mine actually does not. But whenever she does, it's very important that I have access to all the tools that I have when I'm in office on my laptop. These are, powerhouses. They're very, very powerful laptops. And at a small scale, we should have an ability to reproduce the problems that you have seen in a multi-host, multi-server environments. So it's very critical, and at least it allows you that it does not impact your system so much so that your profile is very different when you run locally or in a test environments. Second thing is averaging. Time and again it has come. Whenever somebody comes to you and says, yeah, our system can meet these SLAs when it comes to throughput or latencies, you need to ask, is it averaged or is it like for every request? Because in some applications don't care, averaging is good, right? But some applications that are very critical, the averaging is not good because it hides the problem. Same goes with sampling. With sampling your application, you will miss some events that are critical. And you need to make sure, again, that you monitor, track, measure every event that you're processing. And you have to do that in a way that it's not actually stressing your system. And this is a solution that we have built and we ran on multiple hardwares. And the impact of that solution, because of all the APIs, the lightweight data structures, is less than 1%. If we have to measure, it's like somewhere close to 0.5% of the entire resources that you have. GC has a big impact. 8 hours, no GC activities, hits a big spike. That has a big impact on your overall system behavior, especially in a distributed environment, distributed computing environment. And if you have not done so already, I would highly recommend that if you have an application which is latency sensitive, take a look at the Java 7, the release 40. They have some really, really cool features, waste percentage, initial occupancy rate. There's so many tuning and made it very easy to tune as well. And you would like to look at those parameters and how you can tune them to actually make your heap profiles very, very predictable. Third point is watch for the processor sharing the same host. It's like for the entire day the system behaves properly. Something happens at 12 o'clock in the night and it goes down. There's a virus scanner that is running at 12 o'clock. So, if it's not a Windows system, if you're sharing your host, something with a small HTTP server, that could misbehave. And CPU-bound applications like ECE, they are sharing CPU cores with other activities on your system. So you don't want other processes to hog away your resources. And needless to say, always run long duration tests. I would assume everyone does, right? Any problem that you would not see in a 3600 seconds will appear in 8 to 10 hour tests. The things that will not appear in a 10-hour test or a weekend test will appear in a 48, 72 hours a week runs. So it's always recommended that we do long-running tests to really know what is your application behavior, and more so if it is a pure Java application. I'm pretty sure you have hundreds more, but those are the more critical ones that we could. I thought that we would put in on the slides. Okay, so I think this is the last slide, and I'll let Diana decide how we did.
Yeah. So this is the last slide at last, and maybe some of you still remember this slide. These actually are functional requirements we outlined just in the beginning of the presentation. So let's see whether what we told you actually addresses these original requirements. We got the detailed insight about our performance with the help of granular performance reporting and latency percentile report. Now we know about every single request and the latency of every single request. We got the view over time with the help of combination of granular reporting and the use of monitoring dashboard. Now we can get an idea about our latencies at every moment in time. We got reporting with the help of monitoring dashboard. The method breakdown, the aspected solution, permits us to detect bottlenecks. And finally, we got the view of a system as a cohesive unit with the help of the monitoring dashboard, where we got a single view of every important characteristic on one page. So this is our solution. I think we're pretty much used all the time we have. So thank you for coming. We hope you find it useful. We hope you can apply this in your own distributed Java application. So thank you. We'll take your questions. I think you can come up to us. Our engineering team is here as well. Our architects are here to answer your questions. Thank you.